Okay, this is synchronous week. I don't know what it is. 11? I think we're week 11. Better figure it out. Yeah, week 11. Okay. Today, I'm going to talk to you about a couple different tests to determine whether your series will converge or diverge. But as I mentioned last time, we're moving out of this territory where we're going to be able to find the sum of a series. We're really just going to focus on, does it converge or does it diverge, and just figuring out techniques for being able to ascertain that information. All right, so first things first, we are in section 8.3. Now, we're going to talk about properties of series. I'm going to do this first. Properties of series. And then we're going to focus on series with positive terms. And the integral test. I know there's a lot. Integral test. And just when you thought you weren't going to have to do any integration in this chapter. Okay, I've got some like too much light going on here. Let me see if I can turn this down real quick. I don't know if that was better. Maybe. Okay. It's been a while since I've done this down here. Okay. Hopefully that'll work well. Excellent. The first thing I want to talk about here, and like I said, in the last section, we were splitting up terms of series, and I was mentioning that there were properties for this. I'm going to give you those first. Properties of series. So these are in your book. I want to make sure we talk about them so that I don't forget to talk about them. This is for the sum and difference of convergent series. And again, I feel like you guys have seen these types of properties over and over again, but it's nothing that you can assume until I actually tell you that, yes, this is fair game. So I know you feel like, okay, yeah, I get it. Sum and difference, we can do this. I'm telling you right now that you can do this because we have a theorem for it. So if your series from k equals 1 to infinity of a sub k is S, and you have another series from 1 to infinity of b sub k equals t, are two convergent series. Then the series from k equals 1 to infinity of a sub k plus b sub k. You know what, we're just going to say plus or minus because I don't want to write that twice. Just like you, sometimes I don't want to write excessive amounts of stuff. Also converge. So we can take the sum or difference of two convergent series, and then we would say that the sum or difference of that series itself would also converge. Now, we would also then be able to just make this statement that the series from k equals 1 to infinity of a sub k plus b sub k, and again, I'm just going to go plus or minus just because I think you guys get the gist of this, is going to be a sub k plus the series of b sub k, which is going to be, plus or minus s plus or minus t. Okay, so we have just that we can sum the series separately, or we can sum it all together up in one series. So I just want to make sure I give that to you as a property. We can do something similar with the constant multiple. Again, you've seen these properties with other things, even, going back to derivatives and integrals. But we're talking about them now in terms of series, which are new to us. So the next theorem is about a constant multiple of a series. Let C be a non-zero real number. If your series from 1 to infinity of a sub k is equal to S is a convergent series, then the series from k equals 1 to infinity of C times a sub k also converges. And then we can do something similar with the constant multiple that we would do in other situations. We can say that our series from 1 to infinity of C times a sub k would be equal to C. And of course, we're assuming here that Z is a non-zero real number times the sum of the series from 1 to infinity of a sub k equals C times S. Okay, and we've talked about what happens if they converge, but if the series from k equals 1 to infinity of a sub k diverges, then the series from 1 to infinity of C times a sub k also diverges. So what this means is that multiplying a series by a non-zero number doesn't affect convergence or divergence, even if that non-zero real number is, I don't know, like a million or 1 over a million. It doesn't matter. If your series is going to converge or diverge, you can multiply it by any constant you want. That's not going to affect whether it converges or diverges. So these are properties that are available to you to use. We already sort of used the sum and difference for a convergent series when we were talking about geometric series. So we've sort of used that one already, but you may decide to use them. You may not use them. You probably will use them. You probably have used them already, but I just wanted to make sure we discussed them. So there they are. Those are your properties of series. Okay, another really important theorem, like really important, and we're going to go over this next, is called the nth term test for divergence. Your book technically calls it the test for divergence, which I'm really totally happy with. Some books call it the nth term test, and I like that they include the divergence test because it really only makes a conclusion about whether or not your series diverges. We're going to talk about that next. All right, so this is on page 602, and it's a short theorem. We love short theorems. So this says, first of all, this is leading up to your theorem for the test for divergence. So these two sort of go hand in hand. This is the piece that sort of leads into that. If the infinite series and the series goes from 1 to infinity of a sub k converges, then the limit as n approaches infinity of a sub n equals 0. Okay. I'm getting in real close because I really want to make a big deal about this because this is a really important statement. The most important part about it is that it goes one direction, not the other direction. If the series converges, the limit is 0. If this, then that. This doesn't go the opposite direction. We can't say that if the limit of a sub n as n approaches infinity is 0, then the series converges. That's not what it's saying. That's not true. I once had a student, I kid you not, on a test. I think I've had this happen twice actually. They answered every question for every series based on the limit. So they took the limit, and if it equaled 0, they were like, the limit's 0, therefore the series converges. That's not true. You cannot do that. I'm going to give you the second part of this, and that's really the test that you're going to be using, but it goes along with this. Theorem, test for divergence. I'm even putting it in all caps. You see, I'm starting to do crazy things like that. I even put an exclamation point on it. Test for divergence, because I want to make sure that we understand this is not a test that tells you whether or not your series converges. It's a test to tell you whether or not your series diverges. The infinite series from k equals 1 to infinity of a sub k diverges if the limit as n approaches infinity of a sub n does not equal 0. Okay, so this is a direct conclusion from the previous theorem. If the series converges, then it must be the case that the limit is 0. The series diverges if the limit is not equal to 0. So the way you're going to use this test is if I give you a series and I say, does this converge or diverge? One of the first things you can do is take the limit of a sub n. If the limit's not equal to 0, you can automatically conclude that the series diverges. Now, if the limit is equal to 0, you can make no conclusion. So I'm going to give you this little corollary. The limit as n approaches infinity of a sub n equals 0, you can make no conclusions regarding convergence or divergence. Okay. If the series converges, the limit's 0. The series will diverge if the limit's not equal to 0. However, if the limit is equal to 0, maybe it converges, maybe it diverges. We don't know. We can't say. We need to apply another test. So that's the way you're going to use this test. You're going to take the limit. If it's not equal to 0, you're going to make a conclusion that your series diverges. If the limit is 0, try another test. Okay, so I'm going to give you a plethora of tests throughout this chapter, mostly through section 6 is where we're going to be doing all these tests. So this section 4, 5, and 6. In section 4, we'll work on comparison tests, which are outrageously useful and some of my favorite tests. In section 5, we'll talk about series that alternate, that have alternating pieces to them, like that -1 to the nth piece. And then in section 6, we'll focus on ratio and root tests for a lot of series that you'll be dealing with that have radicals in them or some sort of rational exponents. But, you know, including but not limited to those types of series. Okay, so that was a really important theorem, the test for divergence. I'm going to give you an example of how to use that now. I'll actually do parts A through C of this just so that we understand how it works. Example 1. Use the divergence test to attempt to make a conclusion regarding divergence, I should say. I'm not going to make any conclusions regarding convergence. The first one is the series from 1 to infinity of 3k divided by 4k plus 1. This is not to the kth power. This is 3k over 4k plus 1. All right. So what I'm going to do is I'm going to take the limit of a sub n as n approaches infinity. And I'm going to see what happens. If I get 0, I'm not going to make any conclusions. If I don't get 0, then I'm going to go ahead and say that it must be the case that my series diverges. So we're going to take the limit as n approaches infinity of 3n over 4n plus 1. Remember, you can use that rule from algebra that states if the degrees are the same in the numerator and denominator, that the limit is the ratio of the lead coefficients if n is approaching infinity. 3/4 does not equal 0. And because 3/4 does not equal 0, we can say that our series diverges. So we're going to say, hence, the series diverges by the divergence test. There we go. Done. That's how you use the divergence test. Let's do another one. Oh, and by the way, when I made this conclusion, I don't need you to write like complete sentences and do full explanations. What we're really working into today is using a test to make a conclusion and showing that test being used, showing the conclusion, and then we're just writing down what it was and what test you used. When I give you your exam over chapter 8, when I ask you about convergence or divergence of series, I'm going to ask you to tell me what test you used, and then I'm going to ask you to show me your work using the test, and then make your conclusion. So you're going to tell me that you used the divergence test at some point, whether you say it here at the end or whether you just write down divergence test. You're going to show me that you applied the limit, and you're actually going to write down the limit as n approaches infinity of a sub n, and then show me that it doesn't equal 0. Don't just say equals 3/4. Show me it doesn't equal 0. Then make your conclusion, which is that the series diverges by the divergence test. This is what an answer on your exam should look like. B, this is the series from 1 to infinity of 2 over 7 to the nth power. Now, if this series looks familiar, it's because you've done a ton of these already from 8.2 when we were talking about geometric series. And if you're like, wait a second, geometric, this doesn't look geometric. Oh, we're going to make it geometric. Oh, okay. I did that thing that I said I was going to do, which was mixing up the n's and the k's. K. Okay. Okay. It's because when I wrote down what I was going to do today in my plans, I originally wrote n, and when I turned it into a k, it still kind of looked like an n. Anyway, either way, we can tell by looking at this that this is going to be a convergent geometric series. But if I was to try to use the divergence test to make a conclusion regarding divergence, I would take the limit as n approaches infinity of 2 over 7 to the n. And this would just be 2 over 7 to the infinity, which would be infinity, and I would get 0. Now, remember, if the limit is 0, that does not mean that we have a conclusion that it converges. This does not mean the series converges. It just means the series, it just means we don't know. Actually, it doesn't really mean anything. If we get 0, we don't know. So we're going to have to use another test. So we already rewrote this into a geometric series. We can say that r equals 1/7, which is less than 1. Remember that for a geometric series, if we're dealing with the absolute value of r being less than 1, then the series is going to converge. So at that juncture, if you were to, I mean, if you want for every single series, you can try the divergence test first. If you get a 0, oh well, move on, do something else. You'll get 0 a lot. 0 is not conclusive. But when we say try another test, that just means use something that you know about what type of series this is. If it's something really straightforward like this, where it's geometric, you already know that it converges. We can say that it's geometric with r equals 1/7, hence the series converges. So we use the divergence test. We weren't able to actually glean any information from that. Then we used another test, which is geometric series with r equals 1/7 to say that it does converge. And I'm not asking you in this case to find the sum of the series. And in a lot of these instances, there's going to be more than one method for you to determine whether or not your series converges or diverges. So I cannot force you to find the sum of the series unless I'm specifically asking you to do that, and then you're using that process in there. Okay, we'll do one more using the divergence test. This will be C. This is the series from k equals 1 to infinity of k cubed plus 4 divided by the cube root of k. All right. Now, I want you to start getting a sense for what you're looking at with these things. Notice, for instance, that k cubed is in the numerator. The numerator is going to grow much faster than the denominator. So the cube root of k is going to grow pretty slowly, but k cubed is going to grow quickly. These are the types of things I want you to be thinking about when you initially look at the series, because it's really going to help to guide the way that you think about this. In the next section, we'll be thinking about stuff like this in terms of comparison tests. Right now, you can use an nth term test for divergence, which actually is a good method. And this is, this test that you're going to take on chapter 8, this is going to be another instance where there are going to be several different methods for doing the same thing. You might have noticed on your chapter 7 test that some of you guys did some exercises completely different than the way that I did them on the key, but they were great. Like most of you did number 1 differently than I did. And then when I saw it, I was like, oh yeah, that was a good method for doing that. It was just different than the way I did it. As long as your method is valid, you're good. Unless it's something that I've never taught that's really bizarre and random, that is always a little bit suspect. But any of the methods that we cover here are fair game. You're going to have a bunch of different ways of doing the same thing. All right, so let's go ahead and we'll take the limit as n approaches infinity of n cubed plus 4 divided by the cubed root of n. Now, if you remember from Calc 1, we talked about how to find these limits at infinity. Remember with this radical, usually you end up, if you try to use L'Hopital's rule where that radical keeps popping back and forth in its position in the fraction, you can actually simplify it. What you can do, however, is a method from Calc 1 where we always divided by the highest power that you saw on the variable in the denominator. So what I would do if I were you to find this limit is divide the numerator and denominator by the cube root of n, because that's the highest power that you have in the denominator. And part of the point of this is just to get those variables into the denominator so that you can hopefully get some terms to zero out. Now notice in the numerator, when you divided that quantity by itself, you just get 1. In the numerator now, we have n cubed divided by n to the 1/3 plus 4 divided by, well, you can leave it as cube root n in that case. And then you just need to simplify this term. The denominator is 1. You don't have to rewrite it here. Remember, if you are dividing and you have the same base, you subtract the exponents. 3 minus 1/3, well, 9/3 minus 1/3 is 8/3. And now you can see that even though you're going to get this term to zero out when you take the limit as n approaches infinity, this term is going to approach infinity. So infinity plus 0 is infinity. Because infinity is not equal to 0, that's a great conclusion for us. That means that our series diverges. I'm going to say hence the series diverges by the divergence test. So if you're looking at the series, you feel like, I think this is going to diverge, eyeball it first, determine if your limit's going to be 0. If you think your series is going to diverge, but it looks like the limit as n approaches infinity is going to be 0, then use another test. But if you're feeling like I'm going to take this limit and I'm going to get something that's not equal to 0, I think this is going to diverge, do it. That's what that test is for. So it's a really useful test. I sometimes forget to use it, but it's easy to apply. And sometimes I'll put a question on a test and a student will use this on it and it works because the limit's not equal to 0. It wasn't the way I planned for you to do it, but it doesn't matter as long as it's valid. Okay. All right, so I talked about your properties. I gave you those theorems. Let's see. Wonderful, wonderful. I'm trying to get through the easier stuff in 8.3 first, and then we'll focus on the integral test. Not that the integral test is that hard. Technically, it's just a new spin on old information. But yeah, let's talk about P-series first, because P-series is also very easy to apply. And then we're going to be looking at a lot more P-series in 8.4. So you're going to see them a lot in the next section. Okay, but first of all, I'm going to give you the definition for a P-series. Now, if you'll remember, in the lesson for 8.2, I defined for you the harmonic series, which was the series from 1 to infinity of 1 over k. And we said the harmonic series diverged. But the P-series is more of a general variation on that definition. Oh gosh, I wrote out the whole word. P-series. Okay, a P-series is an infinite series of the form k equals 1 to infinity of 1 over k to the p power. So it's not k times p, it's k to the p power. So this is going to be 1. So if we let k be 1, 1 to the p is still going to be 1. If we let k be 2, we're doing 2 to the p, and then 3 to the p, so on and so forth. Then you'll have n to the p, so on and so forth, where p is a positive real number. Note that if you let p be negative, then we're dealing with a negative exponent and it's no longer sitting in the denominator. You no longer have a p series. So it must be the case that p is positive. All right, so this is what a p-series looks like. Now I'm going to give you some information about the convergence or divergence of a p-series, which is going to be very dependent on the value of p. So here's your theorem. This is something you're going to use all the time, this p-series test, all the time, all the time. Convergence, divergence of a p-series. All right, the p-series converges if p is greater than 1 and diverges if p is between 0 and 1 inclusive. Now, if p equals 1, you have the harmonic series. Which we discussed in 8.2. So if p equals 1, then you just have 1 over k. And we talked about how the harmonic series diverges. The p series will diverge if p is a value between 0 and 1, and it converges if p is greater than 1. So don't get this mixed up with your geometric series because we always think about the geometric series converging for values that are less than 1. I wouldn't think about this as being the opposite, but if you want to think about it being the opposite, maybe that'll help you to remember it. So in this case, if p is some sort of proper fraction, some very small number, your series is going to end up diverging because you're not dividing by numbers that are large enough to eventually drive the terms of this series to 0 out quickly enough. But if p is a greater value, then the denominator is going to grow more rapidly, which means the ratio is going to decrease faster, and then you're going to be just adding smaller and smaller terms, small enough that you're eventually going to get that series to converge to a value. You don't know what value, but a value. We're not going to be finding the sums of p series in here. All right. The p series themselves are very easy to work with. When you see them later, it'll mostly be with things like comparison tests. But I will give you some examples of how to use the p series. Super straightforward. The first one will be from k equals 1 to infinity of 1 to the 4th root of k cubed. I know I wrote an n, but it's okay. Now, this is a situation where you have a p series, but like so many other situations, it might not be glaringly obvious. So you're going to have to rewrite it so that it looks like a p series. So when you rewrite this, we must, it's going to make a huge difference. If you don't, we must write this correctly, meaning that we need to remember how to write our rational exponents, converting back and forth between these radicals. Remember, the index of your radical is the denominator. The numerator is the exponent. So this is 1 over k to the 3/4 power. Now, if you accidentally screwed that up and wrote your radical wrong, and you wrote it as k to the 4/3, well, you would then have a convergent p series. But you're not going to screw that up because that's an algebra problem. And you're going to write it correctly. And you're going to get 1 over k to the 3/4 power. And 3/4, gosh, did I say that backwards? If you write k to the 4/3, you will get convergent. I can't rewind. You guys can. Anyway, but you have 3/4, which is between 0 and 1. Therefore, your series will diverge. So it makes a big difference if you accidentally rewrite this the wrong way. So let's go ahead and say that we have P equals 3/4, which is less than or equal to 1. You can write it like that. And since we know that, we can say that our series diverges by the, you can say it by the P series test if you want to do that. You could say hence the series diverges. And you can even just say P series, as long as you've told me what P is. You're telling me you're looking at a P series, that's fine. That's good enough. The other one that I was going to do here is another one that's in disguise. This one is going from 4 to infinity of 1 over k minus 1 squared. I think I know what you're thinking, which is that, like, okay, it's k minus 1 squared. Does it make a difference? Officially, you don't have any sort of comparison test at this point to use. You will in the next section. But you can still write this as a P series. Right now, we have this starting at 4. But we can say that if k equals 4, then k minus 1 equals 3. And we can scoot this index back down. And if you're not sure, you can always check this. But if you start this at 3, well, now you can write this as 1 over k squared, because instead of saying k minus 1, you're just saying k, but you're also starting at 3 instead of 4. And notice here that your first term would be in the denominator 4 minus 1 squared, which is going to be 3 squared. And here, again, your first term is going to be 3 squared. Your second term would be 5 minus 1 squared, which is 4 squared. Over here, your second term would also be 4 squared in the denominator. So, you know, you can always check these, but I think, you know, as long as you can, you know, just kind of scoot your index over and rewrite this, I think that'll be the easiest way to go here. So don't make it more confusing than it has to be. If you need to reindex, reindex. Just make sure you go in the right direction. So since you had k minus 1, you went down 1. If that was k plus 1, you would have gone the opposite direction. Okay, but now that we've reindexed, we've written this as a P series, you can say that this is a P series with P equals 2. 2 is greater than 1. So we can say the series converges. Because it's a P series, and you told me already that P equals 2. I told you that, but assuming that this would be something that you would write on a test, you said this. You said, okay, it converges because it's a P series. That's fine. Good. It's excellent. Wonderful. Like I said, we're going to...
Could you try again?
Oh my gosh, I hate when it does that. It's so creepy. Stop it. Okay. Also, it's like almost midnight and it scared me half to death. Ah. Anyway, a little disconcerting. Anyway, that's P series. As I stated previously.
I didn't get that. Could you?
I'm not really sure what I'm saying to prompt that. Okay. I almost don't want to repeat this again because Siri feels like she needs to really listen in. We're going to be discussing this in the next couple of sections and using this with other tests. So the whole idea of P-series, even though you're looking at it and thinking like, oh, okay, this is really easy, this is really basic. Yeah, on its own it is. We are going to be combining this with other tests. So don't feel like, okay, I've seen everything there is to see here. There's so much more to see. Okay, the last test that we're going to be working on in 8.3 is the integral test. I'm going to give you a definition for that. And then I'll show you a couple of examples of how to use this. All right. Let f be a function that's continuous, positive, and non-increasing. On the interval from 1 to infinity, we're going to let a sub k be f of k for all positive integers k. All right, so here's how this is going to work. If the improper integral, I know you thought you were all done with improper integrals, but we're not. If the improper integral from 1 to infinity of f of x dx, kind of nice to see x's again, isn't it? Converges. The series from k equals 1 to infinity of a sub k converges. Okay, now you might be able to guess what I'm going to write next. A little bit redundant, but I'm going to include it here anyway in all of its entirety. If the improper integral from 1 to infinity of f of x dx diverges, the series from 1 to infinity of a sub k diverges. Okay, now, one important note I also wanted to make is that sometimes students think that if the improper integral converges, then the series, okay. Some students think that the value to which the improper integral converges is the same value to which the series converges. We're not being told anything about the sum here, or the value of the sum of the series. This is a test for convergence or divergence, just using the improper integral. Now, I'm going to have a question on your test, specifically asking you to use the integral test to show me convergence or divergence. The reason I do that is because if I don't force you to use the integral test, you're probably going to do everything in your power to use any test other than the integral test, just because it's a little bit longer than other tests. So, but you feel free to use it whenever it applies. Now, we have some conditions here. The function has to be continuous, positive, and non-increasing. We actually have to check those conditions before we use the test. So I'm going to tell you on your test, in the directions, use the integral test to show whether the series converges or diverges. And then I'm going to add on to that, be sure to verify the conditions of the test. I want you to show me that these 3 conditions have been met. I want you to show me that the function's continuous, positive, and non-increasing. Now, you might be like, okay, how am I going to show you that the function's continuous? Yeah, in some cases, you can't really show me that. You're just going to say continuous, check, positive. You're going to look at the terms and you know that if we start at 1, you can look at the value of whatever your function is and show me, okay, like the function always has to be positive. I'm going to do this in the examples. And you're going to say positive, check. And then non-increasing, sometimes we're going to be able to check that off easily. Other times, we're going to have to put a little bit more work into that. But I'm going to go through a couple of examples to show you how the integral test works. And who knows, you might love it and think that it's an awesome test and want to use it all the time. Can happen. I keep moving everything around here, and really it's not working in my favor. Okay. Wonderful. So that's how the integral test is going to work. I'm going to show you some examples now of how we're going to use it. Your first example, I believe we're on example 3. I'm going to try to write your directions the same as the ones in your book. Use the integral test to determine whether the series converges or diverges. So I'm going to just shorten that. Use the integral test to show convergence or divergence. I'm not asking you to find the sum of the series. I'm just asking you to tell me whether the series converges or diverges. Okay, so the first one I want to look at, we'll call it A, is the series from k equals 1 to infinity of 10 divided by k squared plus 9. Now, since we're using the integral test, the first thing you're going to do is show me the conditions have been met so that you know you can use the test. I'm going to show the functions continuous, positive, and increasing. So I'm going to say, is the function continuous? You can even abbreviate it. What you're going to do is just make sure that there are no asymptotes occurring, no gaps in your graph. In this case, you can't possibly divide by 0 because the denominator is k squared plus 9. You can't come up with a value for k squared that's going to be -9. Not going to happen. So you don't need to worry about dividing by 0. Also, keep in mind, even if instead of having k squared plus 9, let's say you had k plus 9, well, k would have to be -9 and k starts at 1. So it could be that you have an asymptote in this function, a vertical asymptote, but not from 1 to infinity or wherever your series starts to infinity. So keep that in mind. Continuous. Check. Positive. Again, we're talking about values of k starting with 1, but no matter what, your denominator in this case has to be positive all the time. You're taking a value, squaring it, so it has to be positive. Adding 9 to it, it has to be positive. A positive divided by a positive is always a positive. Check. Just, like I said, you don't have to actually write out explanations for continuous and positive. You're just basically like writing down continuous, positive, and showing me like, yes, I checked them. This is a point on your exam. This is a point on your exam. Continuous, positive, and then we'll do non-increasing. So what I like to do for the non-increasing part, there are a couple things you can do. You want to show if it's non-increasing, I mean, technically you could show that it's decreasing. You want to show that your k plus 1th term is less than or equal to your k term. Now, sometimes you're going to eyeball this and it's going to be like, yeah, of course, like it has to be this. To show that you're non-increasing, this is what you would have to show. That your next term any term you choose, not just the first term to the second term, but if your first term is k, or if the term you're looking at is k, the next term would be k plus 1. Is the next term going to be smaller than the one that came before it? And in this case, no matter what, personally, I feel like it's kind of obvious that in this case, your denominator would have to be larger. You're taking a larger value, squaring it, and adding 9. If your denominator is larger, then your ratio is going to be smaller. This is enough for me to see that it's decreasing. Not only just not increasing, but decreasing. Check. What you're sometimes going to see, what I used to make students show anytime it wasn't super obvious, was you can always take the first derivative and use the first derivative test to show that it's decreasing, at least starting for some k inside your interval. I'm going to do that for this one, just because you are going to have some where it's not going to be blatantly obvious to you by looking at this. You might have like a variable in the numerator or something, and maybe just looking at this, you wouldn't know. So I'm going to say that we can use the first derivative test to show that f of x equals 10 over x squared plus 9 is decreasing. And I also kind of like to do this just because it's been a long time since you've used the first derivative test, and it's always good practice, right? Always. All right, so let's say we have f of x equals 10 over x squared plus 9. If you want to keep it like this, you can. A lot of times in Calc 1, when we had a constant in the numerator, we rewrote the function like this. You don't have to, but you might find it easier to take the derivative. In this case, you'll still have to use the chain rule. I don't know. It's up to you. If you want to use the quotient rule, that's fine too. But a lot of times when we had a constant in the numerator, we just did this. Okay, so we could say that f prime of x is negative 10. Remember, bring the exponent out front. Rewrite your inside function. Decrease the exponent by 1. Multiply by the derivative of the inside function. So this would be negative 20x divided by x squared plus 9 quantity squared. And then you would pick a test value. Technically, yeah, you could solve and find a critical number at 0. Because remember, if your first derivative is 0, you would have a critical number there. So x equals 0 would give you a critical number. So you know something is happening right there. Well, maybe we should put that down and then talk about looking for a test point to the right of that. Let's do that. Negative 20x equals 0 means that f prime of x equals 0. And if your first derivative is equal to 0, you get this critical number. You get x equals 0. Okay. You also need to worry about places where your denominator could be 0, but in this case, we actually don't need to worry about it because your denominator can't be 0. It's always going to be some constant value. So x equals 0 is a critical number. So whatever is happening to the right of 0, and remember, we don't care about the left of 0 because this function only covers values from 1 to infinity. Whatever's happening to the right of 0, it better show us that the function is decreasing. So you're going to choose a test point to the right of 0. Somewhere inside your interval is probably going to be most helpful. Choose a test point, like maybe x equals 2. 2 is to the right of 0. It's in your interval. You're going to take the first derivative at your test point. And you're going to get negative 20 times 2 divided by, no matter what this quantity in the denominator is, it's always positive. So it doesn't really matter what it is. But 2 squared is 4. Plus 9 is 13. 13 squared is 169. This quantity is a negative divided by a positive, which is always going to be negative, which is less than 0. So therefore, we can conclude that f prime of x is less than 0 on the interval from 0 to infinity. Hence, we know that our function is non-increasing on 1 to infinity. So f of x equals 10 over x squared plus 9 is decreasing on our interval that we actually care about. Okay. So like I said, for this one, personally, I feel like this is satisfactory. This denominator is greater, therefore the ratio must be smaller. But like I said, once you start introducing variables in other parts of the fraction, that gets a little bit more muddy. So if it's not clear, and if you put something on here that's not clear to me on your test, I'm going to wonder, why didn't they show more work? And maybe, no, this is not self-evident. So make sure you know how to do this. If I put a function in your test where like I'm sure you need to use the first derivative test, I'll state, make sure you use the first derivative test to show that your function is non-increasing, and they'll include that piece to it. Okay, so all I've done so far is I've just made sure that the conditions of the test have been met. We said the function was continuous, positive, not increasing. We showed that just in this straightforward way where we were looking at this inequality. And then we showed it again using our Calc 1 skills and the first derivative test to show that the function was decreasing on its entire domain from 1 to infinity. Now what we're going to do is use the integral test to determine the convergence or divergence of the series. And I wonder, what are you thinking by looking at this? Are we thinking convergence or divergence? Because if I can plant some seeds in your mind, if I were you, I'd be thinking that this looks kind of p-series-ish. Constant in the numerator, we're adding a constant in the denominator. These constants are not doing much. Remember, we can multiply by a constant multiple. I can pull it out front, and that's not going to affect the convergence or divergence. Imagine if you pulled the 10 out front, then all you'd be looking at that point is k squared plus 9 in the denominator. And then hopefully you'd be like, oh yeah, this is totally p-series-ish. And we should be thinking that we're expecting this to converge. So let's show that with the integral test. Without further ado. Okay, so remember, all right, we've shown let f be a function that is continuous, positive, and non-increasing on its domain. We did that. We are going to now look at the integral from 1 to infinity of f of x dx. If it converges, our series converges. If it diverges, our series diverges. So we are going to go from 1 to infinity of 10 divided by x squared plus 9 dx, right? Yes, x squared plus 9. Okay. Remember that when you write out an improper integral, you need to use a limit. I'm giving you this look because on your test, a lot of you guys didn't write your limits for your improper integrals, and I took off points because I said that I would. It's part of the definition. All right, so we're going to take our limit, and you choose your variable. We used k a lot before. I don't want to use k again because this was originally presented with the k. Maybe I don't want to use p either because of a p series. Maybe we'll use a. We're going to send a off to infinity. And we'll take our integral from 1 to a. I know now it looks like a 9. I'm already regretting using a. That's fine. We won't use it again. That's going to throw me off and look like a 9. You guys, let's use v. V doesn't look like anything else. I'm using v. And hopefully we won't end up in a part situation. We're not going to. Okay, so now we need to integrate our function. Notice, however, that we look like we're really, really, really close to being in the form of an inverse tangent. We've done quite a few of these. Looks like an inverse tangent. So what we're going to do is we're going to force this to be a 1. I'm going to do a u substitution here. I'm going to rewrite this function. I'm going to divide everywhere by 9. And then we'll get 10/9 times, I'm just going to pull that out front, 1 over x over 3 quantity squared plus 1. Remember, I have to take this fraction and write it as quantity squared. And we're going to add 1. Okay. If you'd like, even you can work on this integral outside of your limit. That's fine too. But we're going to let u be 1/3 x. And then du is 1/3 dx. We're just going to have dx in this instance. You know, I feel like I need to rewrite it so that you can see everything that's happening here. I'm going to go 10/9 times the integral from 1 to v of 1 over x over 3 squared plus 1 dx. 3 du equals dx. And then we'll make our substitution. We'll back substitute and work on this integral a little bit more. 10/9 times 3. And then remember, and maybe I'll just give you the form here. It's 1 over u squared plus 1 du is the inverse tangent of u plus c. Okay, so if the dx is 3 du, now I have everything that I need for my form here, and I can say that this is the inverse tangent of u. I'm not going to write my plus c because I technically don't have a plus c in this instance. Okay. So that's the integral. Now we're going to use the FTC to evaluate it at the upper and lower limits of integration. And then we'll evaluate the limit. So you can divide this out here if you'd like. Now we'll have 10/3 inverse tangent v over 3 minus, if you want, you can pull the 10/3 out front. I'm just going to leave mine right where it is. Inverse tangent 1/3. This is something we actually worked with quite a bit when we were talking about improper integrals, was working on these with inverse tangent forms. We did this a couple of times, and we talked about the inverse tangent of infinity being pi over 2. So if you would like, I mean, I guess we can write it out. This guy is just going to be a constant. There's no need to evaluate. It's not like it's pi over 3 or the square root of 3 over 3. I guess pi over 3 wouldn't even matter in this case. Oh. But it's a constant. It doesn't matter. But the point is you end up getting 10/3 times pi over 2 minus 10/3 inverse tangent 1/3. And then you realize, oh, this is great, because even though we don't need to simplify this constant, we don't even know really what it is or what it looks like, it doesn't matter. All you know is that the limit exists, it's finite. Therefore, the integral converges. So I'm going to say that this is finite. So the integral converges. Hence, the integral converges. And remember, if the integral converges, then your series converges. Therefore, the series also converges. Which we expected was going to happen because it looked very p-series-ish with just a few little constants here and there that weren't really going to change anything or affect the convergence or divergence of the series. So yeah, this is good. I mean, you don't have to simplify this. Once you get it to a point where you can see what's happening, that's fine. You could call it 5 pi over 3, but I mean, especially since you can't simplify this any further, might as well just let it go. Okay. Do another example using the integral test. Maybe 2 more. Oh, I think the last one I called A, so we'll call this one B. Okay, so this will be the series from k equals 1 to infinity of 1 over the square root of k plus 8. Okay, now I'm going to ask you to once again make a conjecture here for what you think is going to happen. This is a good thing to start doing. So imagine for a few minutes that you did not have the plus 8 here. If that was the case, you'd have 1 over the square root of k. Well, that would be 1 over k to the 1/2 power. 1/2 is less than 1. Your series would diverge. So you should be expecting divergence here. This constant is really not affecting that. However, you cannot say at this point, oh, I have a p-series, no big deal, diverges. Plus, I've already asked you to use the integral test. So we're going to use the integral test because it's good for you and it's good practice because I'm going to require you to use it on the exam. Okay, we're going to check 3 things. Is our function continuous, positive and decreasing, or at least non-increasing? Let's try for decreasing first. It's usually pretty easy to show. If you can't force it to be decreasing, then try to get it to be non-increasing. And by the way, usually when you get non-increasing, that's only happening for like, 1 or 2 distinct values of k, 1 or 2 series of the 1 or 2 terms of the series where you might have it be constant for 1 or 2 terms and then it'll start to decrease. So non-increasing just means like make sure that at no point we're increasing towards the end of these as these values get larger. Okay, continuous. Notice the only issue you would have with continuity would be if you let k be -8. -8 plus 8 would give you 0 in the denominator. K cannot possibly be -8. Continuous. Positive. Okay, so starting with k equals 1, you'd get the square root of 9. With k equals 2, you'd have the square root of 10 in the denominator. You have a positive divided by this quantity can never be negative. First of all, it can't be. It's a square root. We're only talking about real numbers here, but we're also starting at values at k equals 1, and we're adding to it. So it's always going to be positive all the time. For decreasing, again, you just want to show that the k plus 1th term is less than or equal to the kth term. So this is the k plus 1th term. And we're just going to show that it's less than or equal to the kth term. And personally, I feel like this is very obvious. I can go ahead and say that this would be 1 over the square root of k plus 9. And yes, the denominator is larger, therefore the quotient is smaller. Check, check. For something like this, I do not need you to go through all that work and show me. You know what's funny? It's not actually funny. But I used to actually make my students always do the first derivative test for these to show me that their function was decreasing. For every single integral test problem, I made them go through and do the first derivative test. You guys are lucky ducks. Not making you do that. If it's glaringly obvious, I'm okay with that. Just show me. For decreasing, you can't just say check until you've actually shown me something. Making sure it's obvious. And this is going to be most obvious when your numerator is a constant. Okay. All right, we verified the conditions of the test are met. Now we're going to go through and say that the integral from 1 to infinity of 1 over the square root of x plus 8 dx is going to lead us to our convergence or divergence. Okay, so let's write this as the limit as, I'm going to use w. Even though I know at some point I'm going to end up using dw probably, but it's okay. We're going to get through it. Got to face our fears. We're going to take the limit as w approaches infinity from 1 to w of 1 over the square root of x plus 8 dx. All right. And then we're going to integrate. If you would like, you can write this as x plus 8 quantity to the negative 1/2 power. And then we'll do a u substitution. Oh yeah, I guess I wouldn't need to do a dw just because I let my upper limit be that. Okay, we're good then. du is dx. So of course, side note, the integral of u to the negative 1/2 du would be increase the exponent by 1, so you'd get to positive 1/2, divide by positive 1/2, and that's 2u to the 1/2. So let's go ahead and fill that in. All right, so we said this was 2u to the 1/2. And then we'll evaluate that from 1 to w. And this will be the limit as w approaches infinity. If you'd like, you can pull this 2 in front of your limit, up to you. W plus 8 minus twice the integral of 1 plus 8. Now, clearly this is a constant, but we're kind of forced to follow what this term is doing in this instance because this term is dragging us all the way up to infinity. And I know what you're thinking, well, it's infinity, but when you subtract off 6, it's totally not infinity anymore, right? No, it's still infinity. I'm just kidding. But you know what? We expected this was going to happen. Remember, we talked about how this looks kind of like a p-series where p equals a half. We expected it was going to diverge. So we will say hence the series also diverges. Okay, so a little bit easier to use the integral test that time around. Let's do this one more time. I know, no, I'm questioning that decision, but I feel like one more example is probably a good idea. And some of you are over there at home being like, really glad you're choosing to do one more example because I really wanted to see one more. It's your lucky day. This is going to be the series from 1 to infinity of k e to the negative 2k squared. I think this is all I have in this section, and then we'll look at some comparison tests, which is awesome. Wonderful. So the three things we need to test are continuous, positive, we'll look for decreasing. We'll be happy if we get non-increasing. Maybe I'll just write that. Okay, continuous. If you're not sure, you might want to rewrite this as k over e to the positive 2k squared. Think about your exponential function here and what it looks like. It is a smooth, continuous curve. I know you're thinking like, okay, well, I know about e to the x, but what about e to the 2k squared? It's going to do the same thing. It's just going to do it faster. You can always graph it in your calculator if you'd like, x times e to the negative 2x squared. But notice that no matter what value you choose here for k, ever, but in our case from 1 to infinity, you don't have any continuity problems here. Like let's say you let k be 1, well, then you have e squared. If you let k be 2, you have e to the 8th. I mean, you're not ever going to come up with a situation where your denominator is undefined. Even if we did, which we don't, have k equals 0, e to the 0 is not 0, it's 1. So you don't have to worry about any continuity issues in this case. The function's continuous on 1 to infinity, or everywhere, but in our case, 1 to infinity. Is it positive? Well, it is positive. We're starting at 1. I mean, now, of course, the numerator, if we weren't starting at 1, if we were including negative numbers, well, the numerator would be affected by that. However, because we're only looking here at positive numbers from 1 to infinity, well, the numerator is always going to be positive because k is starting at 1. So only positive values up here. And then in the denominator, we're just taking e to positive values, and e is going to be positive regardless. So positive divided by positive, positive. Okay, so it's the non-increasing that you need to worry about, because if I were to take my series, which I wrote here as a ratio, k, kept it in the numerator, moved that e to the 2k squared into the denominator so I could have a positive exponent. Let's say we were trying to show that we had decreasing terms here. So we would want to show that the k minus 1th term was smaller. I know I usually did this the other direction, but if we're trying to show that our function is decreasing, then I need to show that the successive terms get smaller, which makes sense because you want to be adding smaller and smaller and smaller values to that. Okay. So if I'm showing decreasing, I want to show that my kth term is greater than or equal to the k plus 1th term. And here's where if you just did this on a test and you were like, check, I don't think I would necessarily agree with you. Now, I would say that this denominator is going to grow more rapidly than the numerator. So in this case, like, if you wrote out a really nice explanation for me in words and said, okay, well, the exponential function grows more rapidly than the linear function. Therefore, if the exponential function has a larger value in the exponent, the denominator is going to grow more rapidly. Therefore, the ratio is going to be smaller. I would probably accept that. But let's say you were working on a random problem on your test and it wasn't an integral test problem and you were like, I have no idea what to do with this. This happens more often than you'd think, by the way. And you're like, I don't know, I think I'm going to try the integral test. And then you'd be like, wait, can I use the integral test? You wouldn't even know. Like, it's one thing if I tell you to use it and you're verifying the terms. It's another if you're just not sure if you can use it at all. So if I were you, I would use the first derivative test in this case. When in doubt, use the first derivative test. So we're going to let f of x be x e to the negative x squared. And I'm not just doing this because I really am enjoying doing the first derivative test. You actually are going to benefit from showing this here. Okay. Now, by the way, this is a product of two functions. You're going to need the product rule when you take the derivative. F prime g plus f g prime. F prime is 1 g plus f, and then g prime. The derivative of e to the u is e to the u du dx. So e to the negative 2x squared, and the derivative of negative 2x squared is negative 4x. So f prime g plus f g prime. And then we'll simplify that out a little bit and get some values here for the critical numbers. So minus 4x squared e to the negative 2x squared. Remember to find your critical numbers. We usually set this equal to 0. You might want to move this into the denominator, or you just factor it out. And then use the zero factor property. E to the negative 2x squared would have to be equal to 0, or 1 minus 4x squared would have to be equal to 0. This one can't be equal to 0. Your exponential function is not going to be equal to 0. Can't be. Don't use it. 4x squared equals 1. X squared equals 1/4. Take the square root and you get x equals plus or minus a half. Now, you don't need to worry about the plus or minus part because all we care about is what's happening to the right of 1/2. Because we're focusing on the domain of our function, which in our case is from 1 to infinity. So who cares what happens to the left of negative a half? Don't care. You shouldn't care either. Does not matter. Okay. So I know that whatever's happening to the right of 1/2, it's either going to be increasing up to infinity or decreasing out to infinity. There's nothing else that changes from 1/2 all the way to infinity. So you're going to pick a test point. You could pick one if you'd like. It technically is in the domain of your function. I'd probably pick 2. 2 is to the right of a half, and it's somewhere inside your interval. So we're going to do a test point, f prime of 2. And if it's less than 0, we'll know that your function is decreasing on that interval. And then we can say definitively that is true. All right, here's your derivative. Use this, use that, it doesn't matter. Pick one. I'm going to use this one, I guess. F prime of 2 is e to the 2 squared is 4 times 2 e to the negative 8th power minus 2 squared is 4 times 4 is 16 e to the negative 8th. Now, e to the negative 8th is going to be positive. However, 1 minus 16 is negative 15. So this is going to be less than 0. So we can say indeed that our function is decreasing. F of x equals x. E to the negative 2x squared is decreasing on our interval. Technically, it's decreasing on the open interval from 1/2 to infinity, but who cares? So I'm going to say actually. Okay. Just so it's not confusing. Okay, once you have that, now we're going to go ahead and use the integral test. Go ahead and set up your improper integral. We're going to go from 1 to infinity of x e to the negative 2x squared dx. We're going to rewrite this as the limit w approaches infinity of the integral from 1 to w of x e to the negative 2x squared dx. Was anyone missing integration? I really was. I feel rejuvenated now. Oh, here we go. Okay. This is a u substitution. I know we maybe haven't done more simply u substitutions in a while, so we don't remember. Let u be, we're going for e to the u, sorry. You're going to let u be negative 2x squared. du is going to be negative 4x dx. Well, you just have x dx. Okay, so we'll do that. And then we'll rewrite this limit as w approaches infinity. And we have an e to the u du situation. So I'll write this as negative 1/4 e to the u. And we'll take that from 1 to w. Again, feel free to move the 1/4 out. I'm going to leave it in. E to the negative 2w squared minus a negative 1/4 e to the negative 2. And then we're going to need to focus on what happens to this term. So this is going to be infinity squared, which is infinity. So this is just going to be e to the negative infinity, which is going to be 0 times negative 1/4, which is still going to be 0, plus 1/4e squared. Sorry, I forgot my equal sign. And we'll just get 1/4e squared. And you might find that for these, you could end up in a situation where you have to use L'Hopital's rule to find the limit. In this case, we did not. We didn't have an indeterminate form. If you had, another variable in front of here, that would have been an issue, but you did not. So we just need to worry about what's happening with that exponential function. This does not mean that our series converges to the value 1/4e squared. It just means that our series converges because the integral converges. So our integral converges. And we're going to say hence, the series converges by the integral test. Okay, that was section 8.3. I want to talk about the first of 2 comparison tests in 8.4, and then we'll call it a day, a night, whatever you're going to call it at this point in time. For me, it's a night. Okay, there's that. Okay, so on 8.3, just to recap, we talked about three tests. Two of them honestly were more important than the last. The divergence test said that if you take the limit of a sub n and you get 0, no conclusion. If you don't get 0, your series diverges. And then we talked about p series, and we said that if we had 1 over k to the p, if p was between 0 and 1 inclusive, then yes, between 0 and 1 inclusive, then your series diverges. If p was greater than 1, your series would converge. Okay. Now, 8.4 talks about 2 different comparison tests. The first one that I'm going to go through tonight with you, the only one I'm going to go through tonight, is the direct comparison test. So I'm going to go through that with you tonight, and then unfortunately the limit comparison test I'm going to have to finish up on Wednesday. Now we're actually on schedule, except for that whole situation that I had mentioned with Thanksgiving. So technically by Wednesday we're supposed to be finishing 8.4 and covering 8.5, which is alternating series. So we're in good shape, you guys. Okay. Comparison tests. 8.4 is officially called comparison tests. You've heard me mention comparison tests a few times now. That's because they're very important. There are 2 of them we're going to go over. The first one is the direct comparison test. The second one is the limit comparison test. Now, I know that when you hear limit in anything, it turns you off. You're kind of like, I don't think I'm going to like this. I'm going to tell you right now, personally, I think the limit comparison test is the test that I use more often than any other test ever. Direct comparison, I don't use that often, but I'm going to show you how it works, and you might find that it works well for you and you use it a lot. And I'll be really happy for you because that's great. Everybody's got what works for them. Okay. Your book kind of lists this out in 2 different theorems. So I'm going to give you the theorem separately the way that they list it. And I'm going to show you how to use these comparison tests. And then on Wednesday, when we go through the rest of this, we'll do the limit comparison test, which I love. And you know I can't wait for that. Okay, theorem, comparison tests for convergence. Okay. If, here's your condition, a sub k, sorry, not equal to, strictly greater there, is between 0 and b sub k for all k, and the series from k equals 1 to infinity of b sub k converges. Here's your conclusion. The series from 1 to infinity of a sub k converges. Okay. Now, the way that I reword this that always resonates with me, I'm going to tell you what it is, and maybe you'll be like, okay, that doesn't make any sense at all, but this is what works for me. If I suspect that my series, a sub k, is going to converge, what I want to do is show that my series is less than or equal to another series that I know converges. So that's the whole point of comparison. You're going to compare your series, A sub k, to a series that you know converges. For instance, a geometric series. You know that a geometric series is going to converge as long as R, your ratio, has an absolute value that's less than 1. You know that your P series is going to converge if you have a P value that's greater than 1. Those are two series that you're going to use a lot for comparison. But it doesn't have to be one of those. You can pick a different series that you know converges, but you might have to do more work to show it. Either way, if I'm looking at my series A sub k and I'm trying to make a conclusion about it, if I want to show that it converges, my goal is to show that my series is smaller than a series that I know converges. So I usually say this. My goal is to show that my series, whatever I'm trying to work with, is smaller than a series that I know converges. And sometimes that's easier said than done, to show that your series is smaller. That's going to be the hard part here in some cases. Just being able to find the right comparison series and showing that. Okay, so that's half of that. The other half would be the comparison test for divergence. All right, so if I'm looking at a series, A sub k, if I can show that C sub k is between 0 and A sub k, inclusive, for all k. And the series from k equals 1 to infinity of C sub k diverges, this is the one that diverges, then the series from k equals 1 to infinity of A sub k diverges. So imagine that your series is A sub k and you think it's going to diverge. You have that suspicion because you've kind of been looking at series. Now you're getting an idea for what's happening with them. You think your series is going to diverge. You need to show that it's greater than another series that you know diverges. Cool. If I'm trying to show divergence, show that my series is greater than a series that I know diverges. Something smells like it's burning, and it's quite possibly this candle that's been on for 12 hours. I'm going to just blow it out real quick because it's a little bit upsetting. Terrific. All right. Did you let this soak in when I was up? Let it soak in. That's really the direct comparison test. Your book doesn't actually call this the direct comparison test. It just has two different tests. One of them is called comparison test for convergence. The other is called comparison test for divergence. And I'm going to show you how they work. Okay. Example, sorry. Example 1. I don't know what I was about to write something. Another theorem, which we certainly don't need in our lives right now. We're ready to apply the theorems we have. Okay, we're going to go from 1 to infinity. I'm going to let this be k because I want to be consistent. I say that now, and then I'm going to go write a bunch of n's. Okay. K equals 1 to infinity. My series that I'm trying to figure something out about is this one. 1 over 2k squared plus 1. Now, the question is, does your series converge or does it diverge? You're like, oh, I don't know, but hopefully you have some ideas, as you should, because this looks very p-series-ish. I didn't just do this one, but I did one that was really similar to it. Notice that this plus 1 constant really not affecting the convergence or divergence, and neither is the 2. So what this resembles is just going to be your p-series, 1 over k to the p, where p equals 2. So I'm going to say that this resembles a p-series. I'm just writing this down right now. This is my informal note to self. I'm going to say that this looks kind of like, and I'm going to do like a kind of like 1 over k squared. So this is my goal. I want to first find a series that I can compare this to. And the goal after that is going to be to show that my series is either greater or smaller, depending on exactly what I'm trying to show. But the first thing is to come up with some sort of series that resembles this. Once you have that, then you're going to say, okay, this is a convergent p-series. Now, I know that for some of you super savvy people, you're going to be like, okay, well, I mean, clearly if the constant and the plus 1 don't affect convergence, then this is convergent and we're good to go. You have to show me this using a test, though. You can't just write out a bunch of words about how you feel about the series and what your thoughts are about the series. You need to show me this with a test. And I know that's very annoying to some of you because you're like, okay, clearly this is going to converge. Yeah, I get it. You have to show me with the test. You must. All right. Okay, it's convergent. So what I need to do, if I'm going to show that my series is also convergent, which it must be, comparison test for convergence, I need to show that my series is smaller than a series that I know converges. So my goal is to show that my series is less than or equal to that one, because I know this converges. It's a convergent p-series. Equals 2. Okay, so we're going to have to show this. And I think part of this we can easily show. So start at the beginning. 1 over 2k squared plus 1. We know that this has a larger denominator than this. Yes, okay. So this is the kind of reasoning that we're going to be working with a lot with these comparison tests. You're going to say, okay, well, clearly this denominator is 1 greater than that one. So if this denominator is bigger, this fraction must be smaller because I'm taking a constant. In each case, I have the same numerator. In this case, I'm dividing by 2k squared. Over here on the left, I'm dividing by 2k squared plus 1. So I'm dividing by more over here. If I'm dividing by more, the ratio is smaller. Okay, so I'm going to even write this down because I'm thinking back now to when I used to teach this in person. And as soon as I would write this down, I would have probably a third of the class kind of doing this at me, like, And when I saw that look, I knew that it wasn't clicking. And I can't see your looks right now, first of all, because we're asynchronous. But also, if we were synchronous, you wouldn't have your cameras turned on and I still wouldn't see those looks. So all I can do is go off my prior experience with students and how sometimes our number sense isn't always exactly in the same place as everybody else in class. Okay, so when you take the same numerator and you divide by a larger number, so I'm going to say divide by larger denominator, then you're going to have a smaller ratio. Okay, so this is true. Okay, now the problem occurs when I try to make this leap. Oh, actually, no, I can make this leap. Never mind. I can use the same reasoning again. I can say, well, okay, if this is 1 over 2k squared, well, 2k squared is greater than k squared. Therefore, the ratio 1 over 2k squared is less than 1 over k squared. Same reasoning here again. So now I've shown not only is my series less than or equal to 1 over 2k squared, but it's also less than or equal to 1 over k squared. We have now officially shown by comparison that our series is convergent. So this is what you're showing on your test. I give you this series, and then you have a bunch of options available to you. By the time you get done with this chapter, you're going to have so many tests at your disposal. So you're going to get an idea for what you think is happening. If you want, write a goal, fine. If you don't, that's fine too. But at least show me some sort of roadmap. Even if you don't say this, you must say this. This is the part that's required. Show me by comparison that your series is less than or equal to a convergent series if you're trying to show that it converges. Once you have shown this, we can say hence our series. And again, you don't have to write all this out. I want to make sure it's super clear. Converges by comparison. And if you want to just say it converges by comparison, fine. You could also say it converges by comparison with 1 over k squared. That is also fine. But you have to tell me comparison because that's the test you used. Not limit comparison, which we're going to talk about Wednesday. So there's a difference. So comparison and converges. These are the important things. And I need to see this very important inequality showing that you have checked that your series is actually smaller than the convergent series. So this is kind of cool, right? Some of you will really get into this. Others will be like, meh, not so much for me. And that's okay too. I told you I didn't like this stuff when I was a calc student. Did not like it at all. Like, what is this? I just want to do integration. Okay. Let's do another comparison series. A comparison test, I should say. There we go. Let's do this one. Example 2. This is the series from k equals 1 to infinity of k cubed divided by 3, k to the 4th minus 1. Now, if you're not sure what you expect to happen, take your series out for a second. You're going to start lopping stuff off. Not randomly. You're going to start taking away things that are not very consequential. Ooh, sorry. For instance, one thing I would take away would be this minus 1. Inconsequential. It's not going to affect your convergence or divergence. So I would say that my series is approximately equal to this one. Okay. Once you lop off that constant, well, now it gets to be much easier to see that you can cancel out some variable factors. And you get something that looks like this. And hopefully we can see that this is screaming out at us as including this 1 over k, which is part of that harmonic series, which diverges. Okay. So we know that our series can be compared to this one. So what we need to show, our goal, is to show our series is greater than the divergent harmonic series. Okay, so if we're trying to show divergence, which is what we're trying to do here, because we've kind of, dwittled this down to saying, oh, this looks kind of like that one, we need to show our series is greater than the divergent harmonic series in order to use a comparison test. So we're going to start to do that. We're going to take our series, rewrite it over here, and we're going to, again, start lopping off these constants. Now, this won't always work right away. And note, by the way, that I wrote these examples so that they would work nicely with this test. That's why I don't like this straight up comparison test, because the examples have to be written just right in order to get it to work just the way you want it to. That's okay. On Wednesday, we'll do limit comparison. You decide. You compare the two and see which one you like better. All right, so I need to show my series is greater. So I'm going to do this. I'm going to start out saying, okay, this must be greater than or equal to this, and then see if that's true. If it's not true, then you need to take another approach. If I'm subtracting 1 in the denominator, the numerators are the same. This denominator is less than. That means the ratio is more than. So this statement is true. If you would like, then you could even say that this is equal to 1 over 3k. Now, 1 over 3k is technically a divergent series. So we've already stated that our series is greater than one that diverges. Recall that 1 over 3k we can rewrite as 1/3 times the series 1 over k. I gave you that property that said that a constant multiple can be pulled out of the summation, or put back into the summation without any effect. It kind of floats around wherever it needs to go. So in this case, we can go ahead and say our series we've just said is greater than or equal to this, which is equal to that, which is divergent. So we can now say, hence, our series from k equals 1 to infinity of k cubed, 3k to the 4th minus 1, diverges by comparison. Now, as long as you've told me what the comparison series is, this is fine. If you didn't actually give me a comparison series, well, we've got some problems there. You would have to say diverges by comparison with blah, give you the series, but you kind of have to show me that anyway, otherwise where's your work? So really this is what I expect to see. I want to see like a thought process. And even if the thought process went on in your head, or maybe your thought process went on down here, that's fine. Sometimes we just do a little trial and error. Maybe it works, maybe it doesn't. This is fine. This is clearly divergent. As long as you've shown your series is greater than or equal to a divergent one, then you can say that your series diverges by comparison. What else do I have here? Oh, yes. Mm-hmm. Mm-hmm. Okay. See, I'm trying to, I want to do one more example and I want to pick a good one. Mm-hmm. Mm-hmm. Okay. That was the one I was going to do. Excellent. Okay. Actually, maybe I should do two more. No, one more. One more is good. Sorry, I had a plan, and sometimes I have a plan and then I change it at the last minute, and then nothing. Like everything's fine. Okay, example 3. Yeah, I'll just do one more, and then we'll call it a day. This will be the series from k equals 2 to infinity of ln k divided by k cubed. Oh, sorry. There it is. Here's your series. Okay. Now, I think looking at this series converges. Now, you would have to show that. But again, if you're going to use this test, you need to make a conjecture first, because there's no point in using a comparison test if you don't know what you're expecting to happen. Because you need to show that your series is either greater than one that diverges or less than one that converges. So what are you trying to show if you don't even know where you're headed? Here's what I'm thinking. Do you remember it was the last asynchronous lecture that we did for 8.1? Gosh, I left the notes up. No, I have the notes. I have the notes. They're right here. I gave you guys a list of different types of functions and how quickly they grow. Growth rates of functions. I have it right here. I did it in 8.1, and it looked like this: growth rates of functions. The natural log function grows very, very, very slowly. Now, n to the p grows a little bit faster. So what we're going to do is we're going to use that idea here to show that our series converges. And if you're not sure, like I said, I mean, think about the fact that your denominator is k cubed. And ln k, I want you to start getting into this habit of thinking of a natural log as being very small or slow moving. And if you even think about the natural log function, yeah, it starts out pretty rapid, but then it just kind of levels out. So for larger values of k, the natural log function is not growing very quickly. So you would be thinking here like small divided by large. This probably is going to converge because the ratio is going to get small very quickly when you're dividing by large values. But you can go ahead and set this up and by comparing it to another function that's maybe linear in this case. You can say that the natural log of k is less than k. And maybe that's a weird concept for you, but think about what happens to these graphs. Let's see if this pops up for me. I think it does. I can't remember what I do down here. Oh, there we go. Okay. I'm going to graph the natural log of x, and I'm going to graph x. And you're going to see what happens to these graphs as x gets large. And it doesn't take very long to see this. So ln x is going to be the blue one. I don't know if it's going to come up as colorful for you on the screen, but x is going to be the red one. So ln x, x. I'm just focusing on the numerators at this point because the denominators are the same. So when you're dividing by the same value, all you're really focusing on is the numerator to look at how slowly or quickly your function is growing. All right, graph. There's our natural log function. There's the x function. So what you're seeing here, well, kind of, your natural log function, even as x is getting increasingly large, does not get very large. But y equals x is always going to have a larger value than the natural log of x all the time. So no matter what, this function is always on top. That means it's a greater value. This inequality holds true because of that. So this might be one of those tools that you sort of keep in your back pocket for thinking about the natural log by comparing it to x. So if you're trying to make some sort of comparison, you can always use the fact that the natural log of x is less than x, or the natural log of k is less than k in this instance. If you're trying to do something like that. If you were trying to do the reverse, your graphing calculator is always a good way to look at these types of things. Like, let's say you were trying to do something with the square root of x, for instance. Notice what happens between the square root of x and the natural log of x. So here's your natural log of x, and there's your square root of x. They actually look like they follow along these pretty similar paths. I might even argue that the square root of x seems like it's going to grow more rapidly because it looks like this distance might actually be increasing over time. If you want, you can even look at your table. The first function is the natural log. The second function is the square root of x. But you can start to look at that for really large values, like 1,000. Your natural log function is still at 6.9078, whereas your radical function is at 31.623. So it even still looks like x to the 1/2 is greater than your natural log function. But, you know, I just want you to understand that you can use your calculator as sort of a tool if you're not sure. Maybe you have an idea of which function is growing faster than another, but your calculator is always a really good way to look at that. Not, of course, an exact measure. Once you get into 10,000, you're seeing now that your log function's still dwindling over here at 9.2103, whereas your radical function's now at 100. So growing super, super slowly. So as you're thinking about these comparisons, just comparing to natural log is always a good idea, because when a natural log pops up, sometimes we don't know what else to do with it. So just start getting an idea of how it relates to functions around it, I guess, is my point. Okay. And then you have that k over k cubed is equal to 1 over k squared. Excellent. So we had a suspicion that this was going to converge because we had a pretty small, slowly growing numerator divided by a larger denominator. So we went ahead and said, okay, well, if this is going to converge, I need to force it to be smaller than a series I know converges. This is a convergent p-series. Because I know this is a convergent p-series, I can go ahead and state equivocally that my series converges. Hence, our series converges by comparison. I'm starting to lose all my letters here. By comparison. So that's how the comparison series works. I don't think you're going to see anything super crazy. Yeah, nothing super crazy that I can think of. I'm going to put up some homework for you from 8.3, talking about those 3 tests we talked about in 8.3, and then the comparison test in 8.4. And then on Wednesday, we'll pick up 8.4 again at the limit comparison test, which I've already told you I love. So you really have something to look forward to on Wednesday. It's going to be awesome. You'll have so many options available to you. And then on Wednesday, after we talk about the limit comparison test, we'll talk about a test for alternating series, where you have these terms that go back and forth as they continue to switch signs. SIGNS. All right. Well, I hope you guys really enjoyed this as much as I did. I'm shocked that I enjoyed this so much. Like I said, this takes me a while to get into this chapter, but maybe I'm finally really enjoying it right now. I always end up enjoying it. It's just a, I don't know, slow start. Okay. Have a wonderful rest of your day, whenever day it is that you are watching this. Get started on some homework. And don't forget, you will have a quiz over this on Wednesday, which is November 3rd. In class, in case I forget to remind you, your drop date for this class, if you want to drop with a W, is November 7th. So that's a Sunday. So just keep it in mind, November 7th. If you feel like you might not pass and you want to take the W, that's the last day you have to drop. Otherwise, you get whatever you get. All right, that's it. Wonderful. See you Wednesday. Adios.